It's a great pleasure to have Professor Aditya Prakash. He has been a close collaborator of our group for a long time. We used to be at Virginia Tech together. Now Aditya has moved to Georgia Tech, and he's been very active in the use of data mining and machine learning for epidemiology, and he's looked at lots of interesting problems of forecasting, inference, control, and so on. So it's a great pleasure to have you, Aditya.
Thanks a lot, Anil, and welcome everyone. Hi, I'm Aditya. I'm an associate professor in the College of Computing here at Georgia Tech. So today I hope to give a quick overview of some of the work our group has been doing in using deep learning and data-driven approaches for epidemic forecasting, and what has been our experience for the past couple of years and how we have adapted it to the COVID scenario right now. First of all, thanks a lot for obviously the invitation to Madhav and Anil. I mean, we are all aware of the well-known COVID trajectories, right? NDSSL and the BI at Virginia also have as a dashboard. There are many other dashboards from other groups as well. So all of them have been trying to look at cumulative mortality, confirmed cases, and different pandemic outcomes. So naturally, CDC started these collaborative COVID forecasting projects, which are more focused on short-term predictions. So these are more quantitative forecasting projects, where maybe the one target is weighted influenza illness count. I know many of folks on this grant are also participating in these kinds of tasks. Then COVID-related mortality per week, and then daily COVID-induced hospitalization. So these are the three main targets which CDC has been pursuing, at least in one group, and releasing them publicly. These are at various levels, national level, state level, and now they are slowly moving into county level as well. These forecasts have gained quite a bit of eyeballs and popularity, in the sense that it's been also featured on these 538, the website by Nate Silver, then also referred to by the CDC director. So in some sense, these are a very public-facing numbers which CDC is releasing from different teams, including where we participate for predicting these targets. So why forecasting? I don't think I need to convince this audience that forecasting is very useful for many different things. Obviously, one of them is resource and budget allocation, ensure preparedness, support decision making, but also I would say even communication, right? So communicating to the public where we are, what to expect. So for those things, forecasting is a very crucial task. I would like to talk a little bit about influenza forecasting, for which we have been involved in the past, and which in some sense folks involved in this flu forecasting have repurposed their tools and repurposed their techniques for COVID, as you might expect. So CDC runs this CDC Flu Site Challenge, which for past several years has been trying to predict influenza-like illness burden in the United States during the season in seasonal influenza. So what is the informal problem, right? So the informal problem is influenza incidence is observed in the current week. So it's very simply stated. You just have to predict some characteristics of the unobserved incidence values in the future. What do I mean by that? So in the picture on the right, you can see the incidences. So this is probably the burden of symptomatic patients in outpatient visits at different hospitals across the country. And you can see that maybe you have observed the curve till the solid blue line, and then you need to predict some characteristics of the curve which is going to come next. In this, at least for this task, CDC uses the network of healthcare providers who report percentage of visitors related to ILI. So this is also using the ILI surveillance network, which again, I'm sure many of us are familiar with. There are many different characteristics which we want to predict here, right? So some of them are peak week, peak intensity, then the next 4. So these are very specific metrics. So it's not just the trend in general, which is usually what epidemiological traditional forecasting has looked into, but it's also more quantitative in the sense of very specific metrics. So you can think of it as an attempt to try to make these forecasting problems very well defined and having more like a data mining, data science kind of tasks, where different methods can compete and have a measurable success. So there are pros and cons of having that, but it definitely has spurred a lot of research in this area. So more formally, we are given historical seasons. So CDC has been collecting ILI like a burden for quite a while now. So we have a lot of data, but not as much data from a machine learning viewpoint. It's still sparse and a data scarce problem, but we have these historical seasons of previous seasons, right? So you have the ILI burden as it evolves through the season. And you have the partially observed influenza incidence curve till week T. And you want to predict, say, the future incidence, the peak week, the peak intensity, the peak time, which is at what time will it peak, and onset, which is when will it cross a given threshold. So these are very well-defined specific problems, right? And the forecasts we give are probabilistic. So there are a bunch of different error measures which are being used to judge how good the forecasts are. Obviously, many different teams participate here from different viewpoints. Many of them are mechanistic, some of them are more statistical, some of them are both mechanistic and statistical, and so on, right? Our approach here was we began this thing by a thought that why don't we use some form of deep learning to do these kinds of forecasts, primarily because deep learning is very good at learning representations of data, right, of high dimensional unstructured data. So that was the main motivation. And we wanted to see how well deep learning does in such a setting, right, where the data is really scarce from a traditional machine learning viewpoint. Our idea was that if you look at the previous seasons, so here I am showing 2010, 12, 13, and 16, the seasons in some sense cluster together, right? So for example, the red and the green look similar. The black and the blue look similar in some sense, right? The idea is that if I have seen the black one and I know that the blue one looks like the black one, then if I'm asked to predict the blue one, then maybe I can just extrapolate using the black one, right? So this is a very high level idea of what we are trying to achieve. Right? So the main idea is that we should use clustering for prediction. So it's not just for figuring out which two seasons look similar, which obviously a lot of people have done, but can we use it in a principled way for predicting some very well-defined targets of the current season? This is not enough. So as the slide shows, it's an incomplete idea. So the other observation we had was that these clusterings are in some sense evolving, right? So it's not like one season looks like the other all the time. The way it looks evolves as the season progresses. For example, here you could see the 2012-13 season, which is in black. And if you compare it with the initial part of the season, it looks much more similar to the 11 and 12 season. Whereas in the middle part, it looks more closer to the 2003-4 season. And at the end, it looks more closer to the 2009 and 10 season, right? So you can see that none of the colored curves completely match the given season. Instead, different points of the curve match better in different points of the target curve, right? So in some sense, this is a dynamic clustering. So it's an evolving clustering. So you have to figure out these evolving clusterings automatically and use it for prediction. So that's the second observation. The third thing which we said was that can we do this in an automatic manner, right? Because in data science, and this is a very well-studied problem of clustering time series in some sense, but many of those methods use very well-defined rigid functional forms. So we didn't want to be bound by those functional forms because it's like saying that the epidemic curve looks like this function, right? So yes, that is, you can approximate it, but different parts of the curve look in a very different way, right? So we wanted to do this in an automatic manner to not rely on as much as on manually fine-tuned features or manually fine-tuned parameters and so on. Hence, we used a dynamic deep clustering algorithm for predictions. I'll go over briefly about what our model was from a big picture perspective, right? But the final thing here is from a machine learning viewpoint, it is also very limited data. So it's not like we have a lot of data. We have 20 seasons of ILI. And 20 seasons is not much at all, right? So it's a really scarce data for learning these deep learning models, which typically are traditionally trained with lots of data points, right? So tens of thousands or even millions of data points in production level systems at different companies, for example. So our idea was, how do we do dynamic deep clustering for prediction with limited historical data, right? So that was the big picture approach which we adopted in this problem. This was a paper we published last year, in fact, with Naren Ramakrishnan from Exogeneous, who's also a part of this grant. Our approach was we forecast these multiple targets, and one of the first two deep learning-based approaches for influenza forecasting. And it performed pretty well in real-time forecasting, and especially for some regions. The first year it participated, HHS one region where we focused our predictions on. If you look at the big picture flowchart, it's like you are given this historical data, you feed it through our deep networks where we do this inferencing or deep clustering, then we use it for prediction, and these prediction predicts different discrete numbers, right? So the peak value, peak time, and onset, and so on. So the main components, I'll do this briefly because I don't want to go too much into detail about the deep learning mechanism here, but rather give you a big picture idea of what the modules are, how we structured this model, and what is each module in some sense trying to do. The first one is the input encoder, which is what encodes partially observed season. We use something called LSTM. So for those who are not familiar with it, it's a long short-term memory module, which tries to remember what has happened in some sense in the past of the sequence to try to predict the future. So it learns a representation automatically. So all of these are end-to-end systems in the sense that they learn these representations automatically. That's one of the main advantages of these methods, right? I won't go into detail, but we are given the partially observed season given by YC. So it's Y1, Y2, YT. So you're trying to learn just encode the best representation for this season. Typically, just encoding this, usually deep learning systems use LSTMs very successfully for time series prediction, but usually this is not enough. because CDC unfortunately revises and updates the data, right? So these are like job employment numbers. You may get a number today, but after 2 weeks, 3 weeks, 4 weeks, these numbers may get updated, right? And they may get revised up or revised down based on whichever errors have been caught. So in some sense, there is a lot of unreliability of the latest data which you're getting from the CDC. And you need to work under this, especially in real-time forecasting situation, you need to work with that unreliable data. The main idea we had there was to assign different weights to different part of the data, right? So in some sense, you're trying to say which part of the data we trust more for today's prediction. Again, we want to do this automatically, not by hard coding which part of the data we need to look at. Deep networks have proven that they have this idea of attention. So we have used some sort of attention of how you can give attention to different parts of the sequence and use it automatically to do the prediction. Hence, in technical terms, we added an attention layer on this LSTM. But even this is not enough, because usually, for example, what you would have usually found, and this has been found in other data science approaches as well, is that you do very well in training, but you don't do as well in generalizing testing for unseen seasons. So we needed to bridge this gap as well. So what we said was that, okay, we are working with really sparse data and we can do overfit the training set, but we may not do well in the test set. So the model easily overfits and does not generalize well. So hence, we need to extract, in some sense, more information from the same data. So we need to extract more structure from the same data. So that was the main idea. So this is where we started with embedding the historical seasons. This is the clustering idea I had said before, that you embed the historical seasons to capture the similarity with the current season, but in some sense, an evolving similarity. The current season, remember, is observed only till week T, which is denoted by this picture here. And the historical seasons have been fully observed. That's the power of the method. So if you are able to cluster the current season and say that it looks the most similar to which of the seasons I have seen in the past, I can use that to do the prediction. What we do is we use snippets of the historical seasons till week T to learn the embeddings. What it does is that says that if I had observed at this point of time in previous seasons, what would I have expected? And how would I cluster the snippet I've observed for the current season with respect to the historical seasons till today, for example? We call this query length clustering because we need to cluster the current season with the equivalent snippet from the historical seasons. So this is the query length data. So we need to learn meaningful embeddings to week T. Here we used an improved version of deep embedded clustering. I won't go into detail here. The big picture idea is that it can automatically cluster different sequences without really force-fitting a clustering loss or force-fitting a clustering function in some sense. So it automatically learns the best embeddings, which will give you the most meaningful cluster. But one main thing to note here is that we are not really using all the data to learn these embeddings. We have compared the current snippet to equivalent snippets from the historical season, but in the historical season, we actually have the entire season. For example, here, we are just looking at week T for all these seasons, but in reality, you have the entire curve for all these seasons, right? And this is really what we want to map. So in some sense, we need to map the embeddings or the clusterings of this part of the season to how it might evolve in the later part of the season, right? So we want to bridge that map and learn that mapping. What we do is we embed the full length historical season separately, not just the query length, which is the current season, and then learn a mapper between the two embedding spaces. This took a little bit of effort to get it right because you want to be careful about what kind of mappers you can learn, what kind of mapping function can be learned robustly, and all those secondary issues. But the big picture is that we are trying to learn the mapping between a query length and a full length clustering. Finally, we have the decoder, which just, so all these things are kind of encoding the task and encoding the input data. And the decoder is what does the predictions for different tasks, right? So for example, for future incidents, you need to use a very specific loss function and a network, right, which can does that kind of prediction, because some might be vector predictions, some might be categorical, and so on. So the task to peak intensity is similar to future incidents, but peak time, on the other hand, we use a slightly different loss function to get it right, which is cross entropy, which has been proven to be useful for such kinds of predictions. And similar in onset, again, we had to do a different kind of loss function. So the basic idea is that this architecture, this deep learning method, doesn't really give you the entire season. So that's what you might expect from a very mechanistic style approach, which might actually give you the entire season as it predicts as going forward. On the other hand, the viewpoint here is that maybe we can do better for very specific targets if we have data and we are able to train robustly on limited data using some tricks. Okay, this is just quick experiments and baselines, experiments which we did to show our method. EB is an empirical Bayesian method, which has been used quite successfully. Influenza forecasting for the past few years. ARIMA is a classic autoregressive method. Just the idea here is that the current prediction depends on you regress the past and use it to predict the current, right? In some sense, a window of the past of the same sequence. Historical is a historical average of previous seasons, very simple method. So KNN selects the top K closest historical seasons to the current season and makes predictions as their average. So it kind of tries to find the closest seasons. But then here, in some sense, you need to define the distant. Right? How do you define close? In contrast, the deep learning method, which we designed, tries to do this automatically without really force feeding the functions. LSTM is a very vanilla standard way of predicting sequences in deep learning. So we use that too, which was recently published without climate and geographical data. So remember, we are just using historical seasons here. Well, very quickly, more results are obviously in the paper, but how do we perform, right? So so our method was called EPD. Not very innovative in the naming part, but it's a deep learning method for epidemic prediction. So we called it EPD. How does it perform in different tasks for the national region? So here are the different methods. Lower is better because it's showing RMSE error. So we did this for other error metrics as well, but I'm showing RMSE. So you can see for different years, right, different seasons, is the EPD. You can see that it performs pretty well and it gives you very low errors. So it outperforms baselines in most settings. It does not do it in all settings, and that is important to note. Especially, it depends on how atypical the season was, so which is kind of expected. So even on very atypical seasons, it is able to generalize well. It's not like it really doesn't do. So for example, right, so 2011, right, 2009, I don't think we show here, but we do pretty well even in those seasons. Now, if we dig a little deeper into HHS regions, right, different regions, how does it perform? You can see that the performance is actually very consistent. So for most of the regions, we perform these baselines in most settings. So that's also a good sign that the model is able to maintain its performance as we drill down and drill up. So again, I believe this is one of the major reasons was because we were able to learn from sparse data. We also checked how does it perform when the data is delayed. So what does that mean? Typically, CDC, there are reporting delays in these kinds of ILI metrics. So the data which you're getting for this week might already be delayed. So you may not get the data for this week. You may get a data only for the 2 weeks in the past. So how do we do that? So today, I don't know what's the value of ILI today as reported by CDC. I know only the value 2 weeks back. So when you're predicting on Jan 15th, maybe you have observed the curve only till January 1st. So that's the data delay arrival. So even here, so we use different error metrics. You can see that EPD's performance is pretty consistent, right? So you look at the red bars for 2, 4, 6, 8 weeks across different seasons. You can see that increasing the delay does not really make it very worse. You would expect that obviously increasing the delay will make things worse, and it does, but it does not make it that worse. You can see that the results are very consistent, and even across when you use different types of error metrics. So which is a good thing. That means the model is again robust and able to capture trends pretty early. One nice thing which I like about this model is that because we do clustering, in some sense, it also gives you why we are predicting. So it doesn't just predict, but it also tells you that we predicted because we found that this season at this point seemed similar to something in the past. So like the January of this year was similar to probably March of 2016 or something like that. So, and you can see when we are given more data in terms of these historical seasons, we learn different clusterings. Right? So for example, here, when you're just looking at 20 weeks of data, most seasons actually look the same, except of course, the 2009 season, which looks very, very different. By the way, all these experiments were before this year's experience. So that's why you won't see 2020 anywhere here. And as we see more and more data, the seasons kind of separate out, right? So you can see when you see 40 weeks of data, it looks like that 3, 4. So 2009 is here. The green ones are all look similar, then the red ones looks which have a slightly later peak. The blue ones are slightly which peak earlier, right? In some sense, it is learning all of this automatically. So in a way which helps you to do the best prediction in terms of a given error metric. So that is a good thing in some sense. So it learns some interpretable embeddings, especially when it's trying to do the prediction. This is all good. So we developed this method. So it was a deep learning method. We wanted to test out how it works in real-time forecasting. It did pretty well, as I said, in many regions. But at the beginning of this year, naturally, as COVID started, one of the first things which CDC wanted to predict was actually continue predicting ILI in presence of COVID. So obviously, this must be obvious to everyone that the WILI curve but this season is very, very distinct from all the previous seasons. And how distinct is it? I mean, if you look at the influenza outpatient, this number on the y-axis and the week, you can see that. So the gray seasons are all the historical seasons, and the black one is what we observed this year. I mean, immediately it leaps out of the page that the black one has 3 peaks, whereas all the other ones had at max 2 peaks.
Aditya, this is Aravind. Can I ask a question?
Sure, of course. Yeah.
Very nice so far, very interesting results. Can you give a little more technical details of what sort of embedding and clustering you use?
The big picture idea here was that we use this, so we improved upon this deep embedded clustering. So the idea is that you have these sequences, we use what is called an autoencoder. An autoencoder tries to encode the data and tries to decode it. And the idea is that the latent representation which you learn for that data will give you these clusterings. So this so that is a big picture idea. So the idea then becomes that how do you minimize, so what kind of loss you put here, and how do you make this work in some sense. So it's an autoencoder with a clustering loss, so at a very high level. It learns these clusterings automatically without really force feeding. And note that this is a part of the same deep learning module. So this is the nice thing here, that it's part of the same deep learning module. So we do end-to-end training. So that means that in practice, that means that it learns the best clustering, which will give you the best prediction, rather than first defining the clustering and then using it for prediction. It learns whatever it needs to learn so that it minimizes the prediction error on the training.
And the loss you use is cross entropy here?
Yes. Exactly. I'd be happy to talk more about
Excellent. Is there a paper available?
Yes. Yeah. So this was published last year at KDD. So I can put that link. Yeah.
Great. Okay,
Thanks. So the WILI curve for the current season is obviously very distinct and different. I mean, which is clearly seen here. For example, there is an uptrend from weeknight onwards in the US national region. And especially if you look at HHS regions where New York is, clearly it just goes haywire. Why is it similar? But a very natural explanation is that there are symptomatic similarities between COVID and influenza. So if you're tracking just this number, you would expect it to change, right? Or in some sense get contaminated by COVID. So historical models are naturally unable to capture this very unexpected trend, right? Because we are now no longer measuring ILI due to influenza. You're measuring ILI which might be contaminated with COVID. So in fact, we did a nice small experiment where we used our all historical models, including Epidemic. And you can see that all of them continue predicting a downward trend, because for them, the season is kind of over. The influenza season is over by that time almost. And you would expect it to just continue going down. Whereas the actual incidence, as we all know, went up and then again went down. So it's an interesting observation why it continued to go down after it peaked again. But I'll come to that later. How would we handle this? So our idea was, again, this is a continuation of this work in Naren's group at PT. Our methodology was that let's leverage knowledge from the historical model, because after all, the way hospitals were reporting are all in some sense similar. There are many biases of how the reports are done, but at the same time, this is a novel situation. So how do we do that? So our idea was, let's leverage knowledge from the historical model, but train a new deep model to exploit new COVID-related signals. So the idea is that the historical data is useful, but what is happening currently can only be given by current data, which are more related to the COVID spread. So that's the main idea, which is that can we transfer knowledge from this historical model to a new deep learning model, which relies more on these auxiliary data sources, and of course with tricks. So all of these deep learning things need some tricks to make it work. So it's as much of an art as a science. What kind of exogenous data sources we use, right? So we used a lot of them, which all kind of touch upon different aspects of what we were interested in. So mobility data was there, then point of care data, so like insurance claims, then line lists, surveys, social media, and many other kind of data sets, right? So some of them are public, some of them are not, so that we had to sign agreements and so on. So all these exogenous data sources touch upon different parts of what we are trying to capture. No one of them obviously can tell you everything what's going on, but our hope was that this covers a broad spectrum of things. For example, mobility should tell us in some sense, give us some indication of social distancing measures. Point of care tells obviously what's happening at hospitals and at point of care, how people are getting treated. Then line lists are the traditional data sets, which I'm sure which are used in epidemiology. Then surveys, KIMSA has these digital thermometers, and then social media data sets, Google searches, and so on. So we call this forecasting COVID ILI because in some sense, this is like ILI in presence of an emerging disease, which shares similarities with it. That's the basic idea of the problem we were trying to solve. So given here, again, we have partially observed influenza incidence curve till week T for each region. But the additional thing which we have here is that you have a set of exogenous data, which is a set of COVID-related features observed till week T for all regions. So what we want to do here is to predict the incidence for the next 4 observations for each region. So it's a very similar task, but in a very different setting because you have this extra data which is coming from COVID-related features. What are the challenges? In addition to that the historical influenza seasons are not big data in the traditional sense of what you think in machine learning, but the COVID-related data is even more sparse because remember, this is an emerging scenario. By definition, you don't have much data on what's going on. You have very sparse, very few timestamps, right? Very few time points in the past, like maybe 3, 4. So if it's weekly, you have only 4 points or something like that for some of these data sets. But many of these data sets are also daily, frequently updated, so which was very helpful for our training purposes. Historical data is rich, but does not capture the effects of COVID. So that's one of the challenges. So we have already kind of alluded to that. And the other thing is that there is also spatial correlation in these signals. That means that some of these signals are correlated, and especially at different regions, they might be correlated in a different way. So we needed to exploit that too. The problem we are trying to solve is how do you leverage both the rich historical WILI data and the highly informative sparse features for COVID ILI forecasting, which is how do you adapt the previous historical model to this emerging scenario. That's what we wanted to do. So we'll release this paper soon on arXiv. The main idea here was we use something called heterogeneous transfer learning. So this is a machine learning approach which tries to transfer knowledge learned in a related setting to your task using some statistical modules. If you look at a very high level abstraction, this is like you have a historical model. For example, here it was our own APD model which we had developed. And then, by the way, this framework should work for other kinds of models too, other statistical models. And then you have this COVID-related module, right, which ingests these exogenous data sources. And then it tries to learn embeddings in a joint latent feature space. So that's the major idea, that what kind of losses and how do you design this so that it can learn the embeddings of these two modules together in a joint space. And then you'd use it for data reconstruction, which is in some sense like an autoencoder, and then use some other losses with attention to do source prediction and target predictions. So your source predictions means the old ILI predictions, the targets are the new situation. But this is a very high level abstraction. So in detail, we needed to exploit spatial correlations, which is done especially in these COVID-related signals using, so this is like we had to use some regularizers and some constraints, right, to make sure that regions which are close to each other have similar prediction. And we use something called GRUs, which are which are well known by now in deep learning, which is used for sequence predictions. Again, the big picture point is that you have these the historical model, which has been trained on historical data, which is EpiDeep in this case, and you have this COVID-related model, which is kind of using new exogenous data sources. So how do you do effective transfer learning between the two of them so that the model knows which one to trust when? That's the most important point, and I'll talk about it later in the results, why that is important, that it should also know when not to transfer knowledge. So this is called sometimes negative transfer. So it needs to prevent negative transfer and also do transfer when it's needed. Here is a quick table of what kind of data sources we relied on. I would put them in 4 different buckets. So line list, testing based, and crowdsourced based in social media. Each of them are related to different parts of what they are trying to measure, from ER visits to social policy and behavioral considerations to symptomatic data and social media activity. It ingests all of these while learning from the historical ILI model. So here is the forecasting performance, right? So again, we used a bunch of different methods to compare us. So many of them were historical flu methods. So as you might imagine, they don't perform well in certain regions. So for example, region 2, I think was New York. So you can see that the historical models really don't do well. Red and the orange are our models. So these are components of our models. So red, orange, and blue, these are the historical models. So you can see all of where that the orange and the red does pretty well in almost all regions. So here is what I meant by negative transfer and also being careful. If you look at the WILI, there are like 2 different states. So here you can see that it goes up, the ILI. So this is very atypical, and then it starts going down. I remember asking this to the folks who are involved at CDC, right, for this. Why exactly is it going down? The idea, so at least for this influenza-like outpatients, it's probably the healthcare seeking behavior is changing here, and people are getting better at separating out these two diseases, right, at that point. So that means at that point, it's better to actually rely on your historical model in some sense. So there are two phases where things are growing, and then things start coming down. So here it looks very different to the historical trends, and here it looks very similar to historical trends. A statistical model needs to adapt to that, and that's precisely what we show here. I don't know whether it's very observable here, but if you look at the RMSE versus week, and these are the different models, you can see that the historical models actually have as expected, they do very poorly at the atypical phase. And as soon as the phase enters the typical regime, it tries to do better. Our model, right, CaliNet, is what you can see that it actually maintains a low error in both those phases, because it can handle the typical regime, but also handle the typical regime, because it knows at the typical point to rely back on the historical model. So it captures trend changes correctly in the current season. So I think this is important, because I hope that this means that the model is nimble enough to adapt. But obviously, it also depends on what kind of data sources you're using, and you need to use the correct ones which can give you value here. One other important thing which we saw was also, like, this shows the ratio of RMSE for different regions as we try to predict further ahead in the week, right? So this is a 1 week ahead prediction. So that means today I'm trying to predict the next week. This means that today I'm trying to predict 2 weeks in the future. This is 3 weeks in the future and 4 weeks in the future. The technique which we used was knowledge distillation. And you can see that knowledge distillation helps improve. So the green means that it is helping improve predictions with and without. It helps improve predictions, whereas versus without knowledge distillation losses, right? So it helps improve predictions, but the help is obviously going down as you try to predict more into the future. So currently what we are trying to focus on also, how do you improve these slightly longer term? So we do pretty well in 1, 2, 3 weeks, but we want to improve our predictions in the 4th week. So it's most helpful in most of the regions, especially in very short-term forecasting. So we also did a simple model ablation, in the sense that we looked at different parts of our model and why those parts of the models are needed. And you can see that in almost all of the regions, our method, which uses all these models, actually performs the best. That means if you remove even a part of the model, the prediction performance will go down. We also did data ablation, where we remove these different types of buckets and try to get a sense of which data sets are important. Here, as you can see, DS1 seems to be very important, because when you remove it, the error actually goes up. So line list data, as expected, is very helpful, but also followed by crowdsource and testing data. Surprisingly, and I mean, maybe this is expected from previous experiences, that using social media data is hard, and we found, at least in this study, that it was the least helpful, possibly because it's very noisy and it's not easy to exploit that. But it's the least helpful, but it's still helpful, right? So it still helps to all of these data sets actually help you to do better predictions. I think I'll skip this about parameter sensitivity, about how do we do that. The bottom line is that it's pretty robust to parameters. So it's not like there are some magic parameters which need to be fit, and only then it can give you good results. In fact, performance is maintained as even when you tune these parameters, orders of magnitude, in fact. So for example, the regional reconstruction parameter, it's like from 0.001 to 0.1, and the results are very, very similar. So what's the bottom line of this work? So the bottom line is that we hope that we have given a principled method, a framework to transfer relevant knowledge from an existing forecasting model, which is based on rich historical data, to one relying on relevant but limited data on recent exogenous signals. That's really the way we are thinking about the contributions of this work. And the hope is that can be extend this to other models and give a more general purpose way, right, where people can just plug and play the historical model and then attach it with these different features, and that can learn to adapt the best of both worlds. So this is for influenza forecasting. So that was influenza-like illness forecasting. So we are also doing mortality and hospitalization forecasting, where we are trying to forecast COVID-related mortality. So this is more directly related to COVID. So the previous one, the expectation obviously there is that it will become more and more important in the fall, when we are trying to predict both influenza and COVID, and both of them will interact in some sense, at least the surveillance of these diseases. So here we are collaborating with UIUC and folks from IQVIA who have these insurance claims data sets. Here, the problem is very similar at a very high level. The problem is now there is no historical data. So that is one of the most important things. Now you really don't have much historical data. you have partially observed mortality and hospitalization till day T, and you have these exogenous data sources. And you want to predict future mortality for the next 4 weeks on a weekly basis, and future hospitalization incidents again for the next 4 weeks on a daily basis. So you want to do these two things, and we wanted to adopt a data-driven approach here again to give a slightly different viewpoint on how powerful are these deep learning networks to learn these targets. So one thing we need to remember is that in this space, deep learning has not really been utilized as much, which makes it interesting. There are a lot of interesting questions about how do you do these things. There are many challenges for this kind of a problem, right? So remember, there's no historical data here. All data you have is the current exogenous data sources, and that's about it. So how do you capture the inherent uncertainty in the data? That is very important because the data is really uncertain. And in fact, that's one of the major lessons we learned, right? So even measuring ground truth and comparing it to ground truth was non-trivial. If you measure your performance this week, maybe next week, COVID tracking or JHU and New York Times will suddenly change their numbers because of some reporting errors, which is to be expected because the situation is like that. But how do you capture the inherent uncertainty data in a principled way and transfer that to probabilistic prediction? And how do you capture temporal correlation between the forecasts? So which is in some sense similar to what we had before. And how do you model effects of these interventions? So the big picture idea is that we captured uncertainty. So this is, we are still writing up the paper, it will be released soon. But the big picture idea is that we capture uncertainty in the data using bootstrapping. So we tried a couple of different things. So there's something called dropout as well in deep learning, but we found that bootstrapping gives you the most robust way of capturing, especially in sparse data here, of capturing data related uncertainty as opposed to model related. And we enforce temporal correlations between these forecasts, right? So that means explicitly, so that means data for forecasting week K and data for forecasting K+1 are actually related, and we enforce that constraint. So this is slightly different from the historical influenza forecasting, which we did, where we didn't enforce these explicit correlations because there we were training for each week separately. The main big idea is that intuition is that there we could do that because you had that much historical data. Here we didn't. When you have less data, you need to exploit more structure and you need to put on more constraints to get something out of it. So that's what we were trying to do here. And we tried to capture the effect of these non-pharmaceutical interventions using these data sources, let's say mobility or these surveys and so on. That was our hope that can give us the effects of these. But important to note that this model cannot be really used for what if forecasting, right? So you cannot just say that, what if I don't do these things? What if the mobility changes like that? Currently these models cannot answer that. So you should think of these as forecast condition to whatever is happening around, right? So one of the things lessons we learned is that we had to train this very frequently and update it in some sense. So you cannot, you need to update it every week and then use it for prediction. And if you do that, then for short-term forecasting, it actually does pretty well. And we are among the top performing things on that portal. So we call this deep COVID. So I won't talk too much about it. But the main thing which we focused on was propagating uncertainties in a principled way so that for each further week of prediction, the uncertainties are propagated in a very principled fashion. I don't know if you remember the models from IHME at the beginning of the epidemic. One of the things which we've observed was very weird, that they were more uncertain for next week predictions than, say, 2 months down the road. So we didn't want to have those kinds of behaviors in our model. So we focused on trying to make sure that the uncertainties which we propagate are very principled, right? And they're principled in a very specific way. And this pays off in the sense that when you measure our performance, both with point predictions, which are like, what is the expected value you predict, and probabilistic predictions, which is looking at the quantiles, both of them actually match very well. And the performance is very robust across both of them. I think the primary reason is that we put a lot of emphasis on this part. The way of enforcing temporal correlations, we use semi-supervised learning here. So this is slightly different from what we did last time. In the influenza thing, it's kind of supervised, right? Because we were trying to do the prediction and we had end-to-end. So here it is not like that because, again, the data is so sparse that you had to resort to semi-supervised learning. So here is one example forecast visualization. So here you have just this is for May 25th, right? Just to give you a sense of what kind of things we are predicting. So this is like cumulative forecast. So at this point of the time, we are trying to predict the next 4 values. And this is mortality. So here CDC assumes, at least in this task, that the data we are getting from JHU's dashboard is the ground truth. And this is like incidence death, right? So you can see these are point predictions, the expected value, and these are the uncertain 95% confidence interval. So this is what is shown on that website. So this is how the predictions would look to public, right? So somebody can just go to that website and this is how it will look like. I feel that this is really helpful, especially for people who are not epidemiologists, right? Just to get a sense of what the models are trying to say in one way, at least for short term. So here's some performance comparison. So this is fresh off the oven results, which I think my students gave to me yesterday, right, yesterday evening. So this is like mean absolute percentage error of the prediction. So these are the point predictions. So you looked at the point prediction and you looked at the ground truth as given by JHU, and you calculate the mean absolute percentage error. And you can see that we are red, so we do pretty well. And especially for 2 weeks, we are by far the best performing method, right? Like for 3 weeks and as well as 4 weeks. And in 1 week as well, we are pretty competitive. And all of these methods are very different, right? So the UT method is more mechanistic, as well as I understand. The UCLA is ODE based as well. This one is ODE based. This one is a hybrid. Again, it's hard to be very specific about the models because they are still under development and things can change. But at least as of yesterday, if you looked at the US national predictions from May to July, you can see that we do pretty well for these short term. So these are, again, important to remember, these are effectively short term forecasts, right? So it's at the maximum a month later. So we found that predicting more than a month doesn't really work well, especially with our method, because people's behavior might change and we need a way to incorporate that. And it's very hard to do that. Then you need to also predict how people's behavior would change if you want to do quantitative comparisons in terms of, like, say, mean absolute error and so on. This is another way of measuring success. So that was mean absolute error. So this is interval 50, which CDC guys also use. This is based on probabilistic errors. So this is trying to look at the quantiles and how the quantiles are behaving and how much weight you give in some sense to the true predictor, to ground truth, which quantile do you place it on, and so on. So even here, if you look at these two plots, it looks very similar. So the trends are similar. The forecasts are, we still perform the best for the next 4 weeks. And it's very consistent compared to the mean absolute. So I think one of the major reasons this is happening is because we quantify and propagate uncertainties in a very principled way. So note that in mechanistic models, maybe you can get these uncertainties for free in some sense. You can just run multiple simulations or multiple things. But in statistical models or the deep learning models, that is harder to do. So that's why we need to pay more attention to doing that in a principled way. There were many challenges. So this is good, and we are participating in it. So we give these weekly predictions. It's displayed on these boards. What are the major issues, right, which we felt? So one of the things was data quality challenges, which, the backfill issues. Things change without notice very quickly, and it's very hard to predict those changes in some sense. And CDC signals, like even excess deaths and hospitalizations ratio, they have a huge amount of backfill, I think, because the situation is so chaotic. The other problem is that there's a lot of missing and unreliable data, and the data is not standardized across different states. So, for example, many states do not report incidence hospitalizations. Some states report unreliable hospitalizations. Some states report total hospitalizations, not the new ones. So there are a lot of these subtle things which are different, and you need to be very careful about what kind of data you're using and understanding that where is it coming from, what does it mean, and even observing how reliable that data is over a few weeks before even using it in your model. So that's one big lesson we learned, especially in such a situation, right? What is a summary of the deep COVID model? It is actually pretty fast. It's scalable. So that's one thing I didn't really focus much on. To a computer science audience, probably I would have focused more on the scalability and how do we train it very fast, but it's capable of ingesting a large amount of signals. So we have a very large pipeline, which is looking at very heterogeneous data sources. So it takes quite a bit of effort to get that right. And then it's easy to adapt to target and time resolution. So like if you want to train it for different regions, so that's very easy. And my students, so we have access to a very big server. We do that. And it's pretty simple. As far as deep learning models go, it's not that complicated, especially because there's not much data to in fact bridge. Yet the simple things which we do get pretty well, and it's pretty competitive. I would caution against the performance results because, as I said, the ground truth itself can change. But even today, if you look at the ground truth and the performance, we are the best in many metrics, next 4-week prediction of the past. The lessons being learned is one thing is that definitely we have to keep updating the model. I can't emphasize this enough, that the underlying dynamics is changing, especially the way the data is reporting and all that, and the data and the model parameters need to be updated. And we do the best when we keep updating the model very frequently. As I said, the evaluations itself in the short term are not always reliable. The ground truth data itself is noisy and can be updated. And validation based on recent data may not always work. It's true that in the current validation, it seems we perform very well. But again, I would hold off on having conclusive statements until some time has passed and we have a good data to do that. And I don't have a good answer about how do we go about that. I think one big thing which would be very useful for these kinds of models would be standardized data reporting through different states and agencies, which would be really useful to train these models fast. And the data situation is very chaotic. And this is very hard, right? So for example, we have been working with IQVIA, and also the data is chaotic because they are also trying their best, and it sometimes takes time for some certain kinds of things to show up and so on. So you need to be very sensitive and understand what data you are getting from. One thing which we are actively working on is trying to bridge this now. So this is a good way of learning the statistical deep learning model for trying to predict these numbers, but these are short-term forecasts. So the real effort which we want to do next is which I'm really interested in, and I would love any input from folks on our team, is our bridging this with mechanistic models, right? So we have all these very nice mechanistic models which can really give you these trends and what if forecasting, these longer-term forecasts. So and model interventions as well. So how do you bridge that with these kinds of models? I think would be a very interesting space, which we are really actively working on and are interested in doing. Before ending, I wanted to give a plug for our workshop, which is co-organized by Anil, Shweta, Mauricio from Harvard, Vijaya at Iowa, Adam from Google. I think so. Many of these names will be familiar to this group. And myself, this is on August 24th. This will be a virtual workshop where we are hoping to have very great keynotes and good papers and discussions. So I would strongly encourage, I will send this information to Golda. So I hope that many of you do participate as audience and ask questions. Thanks a lot to my group. So Vijay just graduated and he's off to Iowa. Then collaborators Noreen and Anil are part of this team, Jimeng, others from other institutions, and thanks to all the support. Thanks a lot.
Great. Thanks, Aditya. You can all clap virtually for your talk.
Thank you. Thank you, Madhav.
Aditya, I just noticed Vijaya got a job there at Iowa. That's great.
Yes. Yeah. Thanks a lot, Brian, for
congratulations.
I know you collaborated. Thank you. I think he's joining there next 2 weeks, I think.
Fantastic.
Thank you, Aditya, for that great talk. We have a few minutes before 12:30 cutoff time. So if anybody has any questions or would like to discuss any of Aditya's great work.
A really interesting talk and work, Aditya. One thing you mentioned in the COVID part, the bootstrapping. Can you say a little bit more? The bootstrapping, in some ways, it could lose the structure in that, right? If you're just taking some random subset or...
Right, exactly. So that is what took some time to get that right as well. So you want to maintain some sense the temporal structure of these things, and you also want to do it in a way which maintains correlations across the different data sources. So there are many ways to do that. Yeah, I can tell you more maybe offline. Basically, you're very right. So you want to do the bootstraps in a way which makes sense to give the uncertainties. And if you do it just independently, it doesn't work, and it gives you confidence intervals which don't really make sense. In fact, one of the motivations for that part of the work was when we observed these very well publicized models and the confidence intervals, in some sense, we couldn't understand them because they were larger at the beginning and then they kind of narrowed down, which was really strange, right? Which is what the opposite you would expect from data-driven methods, because there you would be most certain for the next week and then less certain as you go further away. I think that's an interesting data science problem itself. How do you do that? And that is also model dependent. So we also saw that if you do that bootstrapping, it depends on what kind of model you are using to enforce the temporal constraints. Some models are better. So if you use GRU, then you can do a different kind of bootstrapping. If you use LSTMs, then you can do different, and so on.
Okay, thanks.
So it's a very nice talk right there. Got two questions, I guess. One, are these codes something that we could try out? And the second, more technical question is, you use the forecast to drive, right? So you have this feedback loop from the forecast to the next time, which is actually very useful in some ways, but at least in certain cases when there are rapid changes in the events where you suddenly see jumps going on, it would seem that the forecasted values from the past might affect this, it sort of bias in the wrong direction. Do you see that happening at all?
So that's a good point. So that's why, as I said, for the ILI situation, we don't do that because there is enough data to actually train them separately. But for the COVID thing, especially at the beginning, when we didn't have enough data, we had to resort to something like that. So what we have seen is that at a weekly level, if our data signals are sensitive enough, we don't run into that problem. We do run into that problem if you try to extrapolate it too much. So for example, if you predict week 5, 6, 7, 8, then you see a clear degradation. That's why if you see here, I'm not really trying to predict for more than 4 weeks. So till 4 weeks, we perform pretty well. As you can see, the error metrics, I mean, compared to other methods, we are doing pretty well, one of the best for the till 4. But as soon as you go further than 4 weeks, the biases which you suggest start coming into picture. I think one of the reasons we are doing very well is also because of the data sources, that these data sources are pretty sensitive and there are a wide variety of them. And we have a fair bit of effort in trying to understand which ones to rely on. So I think for that, so it is able to capture, for example, short changes. But yeah, I can see the danger to that. But in a very sparse scenario, we don't have any other answer, frankly. So that I would love to talk more if there is some suggestion about, especially in a sparse scenario, without using mechanistic modeling.
Great, thanks.
Maybe just one last question. Irene had put a question in the chat box. So she asked, could you envision a time when this model might be used to forecast at a local or city level, or is it impossible to get sufficient data?
That's a good question. In fact, that's one of the things we are trying to figure out. So, for example, CDC now has going down into county level, and we were wondering how to drill down. I think this can be useful. So we are working also, in fact, at Georgia Tech to do that at a local level here. So it's unclear what kind of data we can get. I think that's one of the biggest issues. So I think this can be useful, but we have a bit of way to go in terms of collecting these real-time data signals. And I'm unclear about that, frankly, because most of the reporting right now already assumes at some level. It's unclear how do we do that. Maybe we need to rely on more digital sources. So that might be one way, because digital sources have a greater granularity at local and city levels as well. Yeah, it's an open question.
So I just want to thank Aditya again for a great seminar today. Thanks everybody for attending. And just a reminder, our next one of these is actually 3 weeks from today. It'll be on August 13th. And we'll have Naren Ramakrishnan from Virginia Tech give a talk. So thanks everybody for coming today.
Thank you very much.
Thank you. All right. Thanks everyone.
Everyone.